Okay, so this is module 1 in the syllabus. So already I have 3 videos on the basics of this chapter. Analysis of laterally unrestrained. So those steps are available in page number 54 to 60 of IS 800. So you can refer. You need not remember any formula. Directly you can use those equations. First we will see what do you mean by laterally unrestrained. That I have explained already in these videos. Anyway, I will just explain here. Suppose if this is a beam, so this is supported or cantilever or whatever it is there. If this beam is supporting a slab above like this. This is a slab, RCC slab, whereas this is a steel beam. The RCC slab is resting on a steel beam. If this is the case, then what happens? In the lateral direction, so for this beam, this is the lateral direction. Perpendicular to the axis of the beam is the lateral direction, this is the axis of the beam. In such a case, since the beam is carrying an RCC slab, it is restrained, that means fixed. Restrained means, the meaning of restrained is fixed. So in the lateral direction, it is fixed. There is no movement, there is no rotation in this direction. Then we say that this beam is called as laterally restrained. So this is laterally restrained. Laterally restrained. That means there is no movement in the lateral direction. Suppose if you don't have this RCC slab, there is no support in the lateral direction, then it is called as laterally unrestrained. So if there is no support in lateral direction, then it is laterally unrestrained. For example, you have a plane like this. In this plane, I will take a space plane, simple space plane, 3-dimensional plane. So these beams, suppose if we don't have anything above this, then if this is open, suppose if this is open, there is no RCC slab there, it is open. So then these beams are called as, laterally unrestrained or laterally unsupported. Open. So in that case, what happens? These beams will be subjected to 3 things. These beams are subjected to bending, shear, torsion. Torsion effect will be there. That means in the case of laterally unrestrained beams, you will be having torsion effect also. So very important. Whereas in the case of laterally restrained beams, you may not have torsion, it may be very less. So that means laterally unrestrained beams, they are subjected to all the 3. So whenever you are designing a laterally unrestrained beam, you have to design for the combined effect of all these 3. So design is done for all 3. Means this. Usually beams are designed for bending and shear, but in this case you will be having torsion effect also. So due to that torsion effect, you will be having one moment, you have to calculate one moment called elastic lateral torsional buckling moment. See the word. Elastic lateral torsional buckling moment. So this is denoted by MCR in the code. in these pages is available, equation is available. So this moment is very important for the design. Just like you are calculating maximum bending moment, WL square by 8, that formula you are using, you know. Like that, we need to compute this value of MCR in the case of laterally unrestrained beam or unsupported beam. So how to calculate this? You see here, there are three things here: lateral, torsional, buckling, and it is elastic. Of course, we are designing the elastic state only. Torsion is also there, buckling is also there. This buckling word normally used in columns. Long columns, they fail by buckling. Okay. So, bending, due to bending, buckling effect will be there. Due to torsion, torsion effect will be there. So, along with torsion, shear also will be there. So, you have studied the strength of materials, torsion of shafts. In the torsion of shafts, so what they found is, whenever a rod or a bar is subjected to torsion, it develops shear stress also. T by J is equal to toe by R. That is the equation, torsion equation, where toe is the shear stress. That means torsion and shear always they will be together. In addition to that, you will be having buckling effect also. This buckling effect is due to bending. Normally, in the case of columns, we call it as buckling. In the case of beams, we call it as bending. So, all the three effects we have to take here. Now, whenever a design is asked or an analysis problem is given, we have to keep it in mind that laterally unrestrained or unsupported beams, so we have to calculate this MCR, very important, which is given in the code. So that is the basic idea here. And all the other details I have explained in these three videos. Please go through the videos and make a notes. Now, there are two types of problems here. One is analysis problem, another is design problem. So they can give anything. Analysis problem means already section will be given. So the meaning of analysis, already the section is given. ISLB, usually for beams, which section we are going to use? ISLB or ISLB or built up section. These are the sections. Normally we are going to be using beams. Whereas in columns, we use ISHB sections in steel. Okay? Heavy beam. So this is medium beam, Indian standard medium beam, Indian standard light beam. One more is the Indian standard junior beam. Of course, that junior beam we are using only for purlins in trusses where loads are less. In buildings, you go for this. Built up section means sometimes you may have to go for an I section with plate. This is called as a built up section, like this, cover plate. This is a built up section. Okay. When the load is heavy, you may have to go for this. In case of bridge girders, you may have to go for build-up sections. So there are so many types of build-up sections you can have. Now, first problem I will take analysis problem where the section is given. This is given. So these sections are given, and they will give the span. Span will be given. Grade of steel will be given. Usually, if the grade of steel is not given, you can assume Fe 410 steel. If they don't give, you can assume Fe 410 steel. So, for Fe 410 steel, the value of yield stress is 250 MPa or Newton per meter square. The value of F2 is ultimate stress is 410. So, that 410 represents ultimate stress. Ultimate stress is always greater than yield stress. Okay. So these values you have to keep in mind. And Young's modulus of steel, normally you know E value, it is 2 into 10 power 5 MPa, Newton per mm square. MPa means Newton per mm square. These are standard values. Even if they don't give, you have to use this one. And rigidity modulus G, you can compute using this. G divided by 2 into 1 plus. This is the formula we can use for calculating rigidity modulus. Normally, mu value is Poisson's ratio. It is taken as 0.3. So these are the elastic constants we are going to use for steel. Now let us take a problem, analysis type of problem. Write down the problem. A simply supported beam of span 4.5 meters. This is an analysis problem. A simply supported beam of span 4.5 meters, span 4.5 meters, consists of ISLB 450, consists of ISLB 450 at 640 Newton per meter. What is the 640 Newton per meter? Weight of that section. It varies from section to section. For a heavier section, weight will be more. That's like 1 meter length alli ಅಷ್ಟು weight ಇರ್ತದೆ, self weight of that section. The compression flange is laterally unsupported. The compression flange, ಅಂದ್ರೆ ಮೇಲೆ top flange. Compression flange is right, top flange. Simply supported beam only top flange is subjected to compression. In case of cantilever beam, bottom flange is subjected to compression. That is why the compression flange is laterally unsupported and unrestrained. Laterally unsupported. Unsupported. The question is, determine the design bending strength of the beam. Determine the design bending strength. So this design bending strength is denoted by MD of the problem. This is an analysis problem. 10 marks that can give for this problem. See, understand here, the section is known here. ISLB, light beam section, with that weight. Span of the beam is 4.5, and we can take it as effective span. So we have to compute the design bending strength. So design bending strength means in RCC also you are going to calculate MR, moment of resistance, isn't that? Same thing here. So this always this MD should be greater than your maximum bending moment or equal to maximum bending moment. So this is the condition for safe design. For safe design, the MD should be greater than M, maximum bending moment. That is the criteria. Always design bending strength means that is the internal strength. Internal strength of the member should be greater than the external force, correct? That is the idea. Then only the structure will be safe. Now we have to find out this MD for this section. Now the thing is, it's a simply supported beam like this. Now we have to compute the capacity of this. What is the bending capacity? Design bending strength, you can say. This is your ISLB 450 at 640 Newton per meter. Please note that this overall depth is 450. Always steel sections are specified with the depth. This 450 mm is the overall depth. This is given by small h. So the thing is, now we don't know what is the load and all. How much load can be applied, then we can calculate after getting the MD value. So this is how much span? 4.5 meters. This is your L. L is the span. You can take the span as effective span. Now let us write down the first step. We have to write down the properties of this section. It is available in the code book as well as in steel tables. We can refer either steel tables or IS 800. So properties we will write. First step is properties of section. So that is the section. This is the section. You write down the different properties. Actually this one is BF, width of flange. This is thickness of flange, PF. This is PW, thickness of web. and overall depth I have taken as D, and one more thing is that depth of bed, that is D from here to here, and this is D. D is different, H is different. D. One more you have called radius at root. So here at the bottom here will be curved shape, arc of a circle will be there, R1. So these are the properties you have to write down. So go to that IS 800, the properties of section, you have to refer IS 800. I think it is there in last page, appendix page 139, or you can use speed tables. If you have brought speed tables, that also you can use. Otherwise you refer from the code. 139 page only. Page number IS 800. 138, 139. That will be the note. IS LB 400. IS LB 400 at 56.9 kg per meter. That is kg per meter. What he has given is kg per meter. Oh, IS LB 450, not 400. 450. So whatever he has given there, that is in kg per meter weight. If you multiply that by 9.81, you will get this 6.1 kg is 9.81 Newton. The properties by write down the properties. ISLB 400 properties in there. Sectional area is there. 450 kan. ISLB 450. So H 450. Overall depth is 450. Amen. Area of the section is there. 83 points. Ready? Sectional area. 83.14. ISLB 450. 83.14 centimeter square. So if you want to convert to millimeter square, 8314. 8,340. Next property is next to BF. It's only what books are without code? So 450 next 170 width of line, thickness of line 13.4. Correct? So BF 170, thickness of line 13.4. TW thickness of line is there. TW is 8.6. 8.6. That's a millimeters. Other stuff is so 8.6. Now after this, after writing the properties, next step is we have to find out D. D don't normalize. D is depth of vector. D is equal to H minus TF plus R1. R1 is the radius at root. What is that? That's straight table. R1 is straight table. Code is other straight table. Just R1. Radius at root D value 68. E formula is going to D continue. H is 450 minus of 13.4 plus 16. That is 29.4. So 450 minus 29.4. 21.6. Correct? Simplify ಮಾಡಿ 450 minus H minus of TF plus R1. Okay? And the quantum 420.6. ಈಗ ಇದಾದ್ಮೇಲೆ ನೆಕ್ಸ್ಟ್ ಏನು ಮಾಡಬೇಕು ಅಂದರೆ ಈಗ ವೆರಿ ಇಂಪಾರ್ಟೆಂಟ್ MCR ಕಂಡುಹಿಡಿಯಬೇಕು ನೆಕ್ಸ್ಟ್ ಸ್ಟೆಪ್. ಸೊ ಪ್ರಾಪರ್ಟೀಸ್ ಬರ್ದಾಯಿತು. ನೆಕ್ಸ್ಟ್ ಸೆಕೆಂಡ್ ಸ್ಟೆಪ್ ಟು ಫೈಂಡ್ MCR. MD ಫೈಂಡ್ ಔಟ್ ಮಾಡೋದಕ್ಕೆ MCR ಫೈಂಡ್ ಔಟ್ ಮಾಡಬೇಕು. MCR ಏನು? ದಟ್ ಇಸ್ ದಿ ಎಲಾಸ್ಟಿಕ್ ಲ್ಯಾಟರಲ್ ಟಾರ್ಷನ್ ಬಕ್ಲಿಂಗ್ ಮೊಮೆಂಟ್. ಅದು ಓನ್ಲಿ ಇನ್ ದಿ ಕೇಸ್ ಆಫ್ ಲ್ಯಾಟರಲಿ ಅನ್ರಿಸ್ಟ್ರೈನ್ಡ್ ಟೀಮ್ನಲ್ಲಿ. ರಿಸ್ಟ್ರೈನ್ಡಲ್ಲಿ ಬರೋದು. ಸೊ ಇದು ಫಾರ್ಮುಲಾ ಇದೆ. ಪೇಜ್ ನಂಬರ್ 54 ತೆಗೆದು ಕೋಡ್ page number 54. Write down that formula. In the case of laterally unrestrained beam, you will be having torsional buckling effect. So we have to calculate the MCR value. MCR value formula is what is the value? Elastic lateral torsional buckling moment 8.2.1. Write down that formula. You need not remember that. Just to write it. So page 54 of code. MCR is equal to pi square EIY divided by LLT whole square. Do not miss any term. Into GIT plus pi square IW divided by LLT square. This is under root square root of this. This is the equation. You need not remember any equation. So it is available. Now you have to see what are these values. And the particular value. It is given there only. Now we know the value of E 2 into 10 power 5 for steel. What is the value of IY? Steel IY value. The properties IY. What is the value of IY and IZ? What is IY? Moment of inertia of this about vertical axis. That is IY. 853 ಇದು y axis. This is y axis. This is z axis, not x axis. We are going to take it as z. So you write down IY value and IZ value. IY value is today for this section 853 into 10 to the power of 4 millimeter power 4. Correct? ಅದು ಸೆಂಟಿಮೀಟರ್ ಪವರ್ 4 ಅಲ್ಲಿ ಇದೆಯಾ? ಅಲ್ಲ 853 into 10 power 4 853 ಮಾತ್ರ ಇದೆಯಾ? ಸೆಂಟಿಮೀಟರ್ ಪವರ್ 4 ಅದು. ಸೊ into 10 power 4 ಆಗುತ್ತೆ ಮಿಲಿಮೀಟರ್ ಪವರ್ 4 ಆಗುತ್ತೆ. ಸೊ we have to convert it to millimeter. ಕಂಪ್ಲೀಟ್ ಮಾಡಿ. ಅದೇ ತರ IZ ಏನು? IZ ಅಂದ್ರೆ IXX. ಅಲ್ಲಿ XX ಅಂತ ಇದೆ. ಕನ್ಫ್ಯೂಸ್ ಮಾಡ್ಕೋಬೇಡಿ. ಕೋಡ್ ಅಲ್ಲಿ Z axis ಸ್ಟೀಲ್ ಟೈಪ್ ಅಲ್ಲಿ X axis. ಎಷ್ಟದು ಜಾಸ್ತಿ 275 0.1 into ಇದು ಕರೆಕ್ಟ್ ಇದೆ ನೋಡಿ ಸರ್ 853 ಕರೆಕ್ಟ್ ಇದೆಯಾ IY ಸರಿ ಓಕೆ so now we have to substitute now ಈಗ ಇದನ್ನ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಬೇಕು IY ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಬೇಕು LLT is nothing but your span 4.5 meters ಈಗ ನಾನು ಬರೀತೀನಿ E value is 2 into 10 power 5 Newton per mm square or MPa IY whatever value there 853 into 10 power 4 be careful every value should be newtons and millimeters units. Next I need LLT. LLT is 4.5 meters, that is the span, which is 4500 mm, convert to millimeters. Then IW, IT, G I have to find out. For finding G, that is this formula, E divided by 2 into 1 plus mu take mu as 0.3, for steel it is 0.3 can take, calculate the G value. G calculate ಮಾಡಿ, use the calculator. Assume for steel mu as 0.3. Poisson's ratio. So E is 2 into 10 power 5 divided by 2 into 1 plus 0.3. This is your G. This is also in Newton per mm square. Modulus of rigidity. G and E is modulus of elasticity. D is modulus of rigidity. So modulus of rigidity is nothing but shear stress divided by shear strain within elastic limits. Since shear effect is also there here, so we have to consider G also. This one is what is the value? G value. You have to
76,923.
76,923.87. Okay. Okay. 76,000. Sorry, 76,923 Newton per mm square. Now we have to calculate two more things. One is IT, another is IW. IT and IW. So for calculating IT, so what is an IT? Torsional constant. Torsional constant. IT is equal to formula is there. I got the formula there. We have to use that formula. After finding all this, then we have to substitute here. We can call this as equation 1. So IT is called as torsional constant. What is the formula for finding this torsional constant? Summation BI TIQ by equal to. This is the formula. So what is this BI TI? That we have to note down. BI is nothing but width of flange and width of web. So here we have to consider there will be two flanges, but here flange here. So this is splitted like this. I section is splitted like this. Okay. Two flanges and one web. So what is the flange width? 170, huh? 170. This is also 170. This is also 170. So I am telling you how to calculate this ID. Thickness is to flange 13.4. This is also 13.4. Then thickness of web 8.6. Depth of web, complete web. You take complete web. So complete web depth is 420.6. So we have to take the depth of thickness of TW. So TW is 8.6. This thing H minus TF. We have to deduct this. We have to take H minus TF. Not D. We have to take H minus TF. H minus TF is HS 450 alva. 450 minus 13.4. That is this depth. We are not taking D. We are taking H minus TF. This side to the 436.6.
So 2 times of
that's how many. Two times average depth. Please note that this 13.4 is ಅದು ಸ್ಟ್ರೈಟ್ ಇರಲ್ಲ ಫ್ಲಾಂಜ್ ಹಿಂಗಿರುತ್ತೆ. ನೀವು ಐ ಸೆಕ್ಷನ್ ನೋಡಿಲ್ವ ನೀವು? ಬೀಜೆಲ್ಲ ಬರ್ತಿದ್ದೀರ ಹೀಗಿರುತ್ತೆ, ಹಿಂಗಿರಲ್ಲ. ಅರ್ಥ ಆಯ್ತಾ? ಅದಕ್ಕೆ ನಾವೇನು ಮಾಡ್ತೀವಿ, ಇಂಥ ಬರ್ತೀವಿ. ಇದು ಟಿ ಎಫ್ ಹೋಗ್ತಾ ಹೋಗ್ತಾ ಹಿಂಗೆ 0 ಆಗ್ತಾ ಹೋಗ್ತದೆ. ಮ್ಯಾಕ್ಸಿಮಮ್ ಇಲ್ಲಿರುತ್ತೆ, ಇಲ್ಲಿ ಮಿನಿಮಮ್ ಇರುತ್ತೆ. ಆವ್ರೇಜ್ ವ್ಯಾಲ್ಯೂ, ಆವ್ರೇಜ್ ಥಿಕ್ನೆಸ್ ಆಫ್ ಫ್ಲಾಂಜ್. ವೆಬ್ಬಲ್ಲಿ ಆವ್ರೇಜ್ ಬರಲ್ಲ, ವೆಬ್ಬು ಸೇಮ್ ಇರ್ತದೆ, ಬಟ್ ಫ್ಲಾಂಜು ಈಗ ಹೋಗಿ ಹೀಗೆ ಬರ್ತದೆ. ಸೊ ಅದಕ್ಕೆ ನಾವೇನು ಮಾಡ್ತೀವಿ, ಇಲ್ಲಿ ಟಿ ಎಫ್ ಬೈ 2 ಇಲ್ಲಿ ಟಿ ಎಫ್ ಬೈ 2 ಕಳ್ಕೊತೀವಿ. ಸೊ ಈ ಥರ ಈಗ ಇದೇನು ಮಾಡೋದು ಗೊತ್ತಾ, IT is equal to ಏನು ಗೊತ್ತಾ, ಈಗ B ಅಂದರೆ ವಿಡ್ತ್, T ಅಂದರೆ ಥಿಕ್ನೆಸ್, ಆ ಥರ ಮಾಡ್ಕೊಂಡು ಅರ್ಥ ಆಯ್ತಾ. ಈಗ ನೋಡಿ, ಫಾರ್ ಫ್ಲಾಂಗ್ ದೇರ್ ಆರ್ 2 ಫ್ಲಾಂಗ್ಸ್, ಈಕ್ವಲ್ ಫ್ಲಾಂಗ್, ಸೊ 2 ಟೈಮ್ಸ್ B ಆಫ್ ಫ್ಲಾಂಗ್ ಎಷ್ಟು 170 ಅಲ್ವಾ, ಇಂಟು 13.4 ಕ್ಯೂಬ್ ಬೈ 3 ಪ್ಲಸ್ ಇದು ಫ್ಲಾಂಗ್ ಆಯಿತು 2 ಟೈಮ್ಸ್ ಪ್ಲಸ್ ವೆಬ್ ಒಂದೇ ಹೋಗಿತ್ತು, ವೆಬ್ದು ವಿಡ್ತ್ ಎಷ್ಟು 436.6 ಇಂಟು ಥಿಕ್ನೆಸ್ 8.6 ಕ್ಯೂಬ್. ಅರ್ಥ ಆಯ್ತಾ. ಸಮೇಷನ್ ಈ ಥರ, there are 2 flanges, width of flange into thickness of flange cube by 3 plus width of flange into thickness of flange divided by 3. This is what we do. Very fast. IT, the value of IT, it will be in millimeter power 4 unit because it is moment of inertia. This is 1 line. Simplify that. Then we calculate IW, warping constant. IW, warping constant. This equation is given in page 129 of the book. Warping constant. This per podium. What is the value of this? You calculate it, huh? Calculate it. ಮಾಡಬೇಕು ಪಟಪಟ ಅಂತ ಸ್ವಂತ ಬಿಡೋಲ್ಲ, ನಾನು ಮಾಡ್ತೀನಿ, ನಾನು ಮಾಡಲ್ಲ, ನಿಮ್ಮ ಹತ್ರ ಮಾಡಿಸ್ತೀನಿ. ಒಂದಾಯ್ತು 365.26 into 10 power 3. Okay, that is the value of IT. Next IW. IW is called as warping constant. Go to page 129. Page number 129 of the code. Another formula. IW is equal to 1 minus beta f. 1 minus beta f into beta f into I by into hf square. Is that one? ಇದು ಅಲ್ಲೇ ಪೇಜ್ ನಂಬರ್ 129 ಇದೆ ತಾನೆ. ಇಲ್ಲಿ ಬೀಟಾ ಎಫ್ ಏನಾಗುತ್ತೆ ಅಂದರೆ 0.5 ಬರುತ್ತೆ. ಇದು ಸಿಮೆಟ್ರಿಕಲ್ ಸೆಕ್ಷನ್ಗೆ 0.5, ಇದು ಸಿಮೆಟ್ರಿಕಲ್ ಸೆಕ್ಷನ್ ಇದೆ. ಸಿಮೆಟ್ರಿಕಲ್ ಸೆಕ್ಷನ್ 0.5 ಇಲ್ಲಾಂದ್ರೆ ಫಾರ್ಮುಲಾ ಇದು ಮಾಡಬೇಕು, ಫಾರ್ಮುಲಾ ಕೊಟ್ಟಿದೆ. ಇಲ್ಲಿ ಎಲ್ಲ ಸ್ಟೀಲ್ ಅಂದರೆ ಸಿಮೆಟ್ರಿಕಲ್ ಸೆಕ್ಷನ್ ಬರುತ್ತೆ, ಅದನ್ನೇ ತೊಂದರೆ ಇಲ್ಲ. ಸೊ ಯು ಕ್ಯಾನ್ ಟೇಕ್ ಬೀಟಾ ಎಫ್ ಪ್ಲಸ್ 0.5. ವಾಟ್ ಈಸ್ ಐ ವೈ ಇದೆಯಲ್ಲ 853 into 10 power 4. ಹೆಚ್ ಎಫ್ ಅಂದರೆ ದಿ ವ್ಯಾಲ್ಯೂ ಆಫ್ ಹೆಚ್ ಎಫ್ ಇಸ್ ಈಕ್ವಲ್ ಟು ಹೆಚ್ ಮೈನಸ್ ಪಿ ಎಫ್. ಅದೇ ಹೆಚ್ ಎಫ್ ಇಸ್ ಈಕ್ವಲ್ ಟು ಹೆಚ್ ಮೈನಸ್ ಪಿ ಎಫ್. ಹೆಚ್ ಮೈನಸ್ ಪಿ ಎಫ್ ಬಂದಿದೆಯಲ್ಲ, ಇದು 436.6. ಈಗ ಅದಷ್ಟು ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿ 1 minus beta f is 0.5 into 0.5 into 853 into 10 power 4 into 436.6 square. ಇದಕ್ಕೆ ಯೂನಿಟ್ ಏನು ಗೊತ್ತಾ, millimeter power 6 ಇದೆ, 4 ಅಲ್ಲ, millimeter power 6. ಬಿಕಾಸ್ IY ಇದೆ, ಬೀಟಾ ಕಾನ್ಸ್ಟೆಂಟ್, IY ಇದೆ millimeter power 4 ಆಗುತ್ತೆ. HF square is millimeter square, so millimeter power 4 into millimeter square is millimeter power 6. This is what it is. This is the value of IW, warping constant. Warping irutte. I have told about warping in mechanics of deformable bodies. Torsion chapter barutade warping. Non-circular sections they will be subjected to warping. Circular sections iralla, non-circular sections, tubular, I section, T section, L section. In those types of sections, will be having warping effect. What is the value of this? IW. Units are 10 to the power 6. Just 406.4 alva 4.065 11. Okay, very high number you get. No problem. So we got IT, IW. Now all these terms we know, correct? You substitute here, substituting in equation 1. Simplify it. MCR in it. So this step is the lengthiest step. Afterwards we can do it easily. So pi square into E is 2 into 10 power 5. IY is 853 into 10 power 4 divided by 4500 millimeter per liter. So this is one term. Second term is GID. G is 76923. 76923 into ID is this value 365.26 into 10 power 3, then plus pi square into E is 2 into 10 power 5. Do carefully because number of terms are more. Into IW is this value 4.065 into 10 power 11 divided by 4500 square. So this entire thing we have to take the square. Do it carefully. There are two terms there. So you can take this as one term and this as second term. You can find it separately and then multiply. You will get the final answer MCR. Try to express this MCR in this form. Some value you get into 10 to the power of 6 because it is Newton meter. E formula 10 to the power of 6 formula. Let's simplify that. Into 10 power 6. So now you have to be careful here. So this into this plus this thing, that is one term. Into this is another term. Then take this one. You can try later on, no problem. I'm going to take point time on that. So this is into 10 power 6. Why I have taken? Because 10 power 6 Newton millimeter is nothing but kilometer meter.
So it's 237 and 287.
237.25. What is the numerical mistake? Check ಮಾಡಿ ಆಗುತ್ತಲ್ಲ. You can check it later. So 237.25 kilometer meter. So this is the value of MCR. Next step, third step. MD find out for that. After finding MCR, you have to find out MD. Actually, MD will be less than MCR. That's the highest value MCR. ಕ್ರಿಟಿಕಲ್ ವ್ಯಾಲ್ಯೂ ಅಂತ. ಕ್ರಿಟಿಕಲ್ ಅಂದರೆ ಮ್ಯಾಕ್ಸಿಮಮ್ ಗೊತ್ತಾ, ಎಮ್ ಡಿ ಡಿಸೈನ್. ಸೊ ಇಲ್ಲಿ ಮೂರನೇ ಸ್ಟೆಪ್ ಏನು ಅಂದರೆ, ಒಂದು ಸೆಕೆಂಡ್ ಗೋ ಟು ಪೇಜ್ ನಂಬರ್ 54. ಅದರ್ ಪ್ಯಾರಾಮೀಟರ್ಸ್ ಹ್ಯಾವ್ ಟು ಫೈಂಡ್ ಔಟ್. ನೋಡಿ ರಿವರ್ಸ್ ಆಗಿ ಹೋಗಿ ಓಪನ್ ಪೇಜ್ ನಂಬರ್ 54, ಆದರೆ ರಿವರ್ಸ್ ಆಗಿ ಹೋಗಬೇಕು. ಅಂದರೆ ಆಲ್ರೆಡಿ ವಿ ಹ್ಯಾವ್ ಯೂಸ್ಡ್ ದಿಸ್ ಈಕ್ವೇಷನ್, MCR ಈಕ್ವೇಷನ್. ನೆಕ್ಸ್ಟ್ ಪ್ರೀವಿಯಸ್ ಈಕ್ವೇಷನ್ ಯಾವುದು, ಲ್ಯಾಂಬ್ಡಾ LT ಇದೆಯಲ್ಲ ಅಲ್ಲಿ. ವಾಟ್ ಇಸ್ ದಟ್, ನಾನ್ ಡೈಮೆನ್ಷನಲ್ ಸ್ಟ್ಯಾಂಡರ್ಡ್ನೆಸ್ ರೇಷಿಯೋ. ಅದನ್ನು ಫೈಂಡ್ ಔಟ್ ಮಾಡಿ. ನಾನ್ ಡೈಮೆನ್ಷನಲ್ ಸ್ಟ್ಯಾಂಡರ್ಡ್ನೆಸ್ ರೇಷಿಯೋ, ಸ್ಟ್ಯಾಂಡರ್ಡ್ನೆಸ್ ರೇಷಿಯೋ, which is divided by lambda LT. ಫಾರ್ಮುಲಾ ಬರೆಯಿರಿ. lambda LT is equal to square root of beta B ZP. So square root of beta B into ZP into Fy by MC. ಅರ್ಥಾಯ್ತಾ? ಇಲ್ಲಿ ಅದು ಲೆಸ್ ದ್ಯಾನ್ ಈಕ್ವಲ್ ಟು ತಗೊಳ್ಳೋದು ಬೇಡ, ಯಾಕಂದ್ರೆ ಅನಾಲಿಸಿಸ್ ಪ್ರಾಬ್ಲಮ್ ಅಲ್ಲಿ ವಿ ಆರ್ ನಾಟ್ ಗೋಯಿಂಗ್ ಟು ಯೂಸ್ ದಟ್ ಲೆಸ್ ದ್ಯಾನ್ ಈಕ್ವಲ್ ಟು. ಡಿಸೈನ್ ಪ್ರಾಬ್ಲಮ್ ಅಲ್ಲಿ ಯೂಸ್ ಮಾಡ್ತೀವಿ. ಇದು ನೋಡಿ, ಈ ZP ವ್ಯಾಲ್ಯೂ ಬೇಕು ನಮಗೆ. ZP ಅಂದ್ರೆ ದಟ್ ಇಸ್ ದಿ ಪ್ಲಾಸ್ಟಿಕ್ ಸೆಕ್ಷನ್ ಮಾಡ್ಯುಲಸ್. ಪ್ಲಾಸ್ಟಿಕ್ ಸೆಕ್ಷನ್ ಮಾಡ್ಯುಲಸ್. ಪ್ಲಾಸ್ಟಿಕ್ ಸೆಕ್ಷನ್ ಮಾಡ್ಯುಲಸ್ ಫ್ರಮ್ ದಿ ಸ್ಟೀಲ್ ಟೇಬಲ್ಸ್ ಅಥವಾ ಬೋರ್ಡರ್ ಸಿಗುತ್ತೆ ನಮಗೆ ZP ವ್ಯಾಲ್ಯೂ. ಆ ಸೆಕ್ಷನ್ಗೆ ISLB ಫಾರ್ ISLB 450 ಸೆಕ್ಷನ್ ZP ವ್ಯಾಲ್ಯೂ ನಿಮಗೆ ಪೇಜ್ ನಂಬರ್ 139, 138, 139 ಅದು ಸಿಗುತ್ತೆ. ಈ ಫಸ್ಟ್ ಬಿಗಿನಿಂಗ್ ಅಲ್ಲಿ ಪ್ರಾಪರ್ಟೀಸ್ ನೋಡಿದ್ರಲ್ಲ, ಅದೇ ಪೇಜ್ ನೀವು ನೋಡಿ ಮಾಡ್ಕೊಳ್ಳಿ. ಈಗ ಆಮೇಲೆ ಮಾಡಿ ಅದು, ಅದೀಗ ಮಾಡಬೇಡ, ಟೈಮ್ ಡೋಂಟ್ ವೇಸ್ಟ್ ಟೈಮ್. ಇದು ನೋಡಿ ಮತ್ತೆ ಮುಂದೆ ಕೊಡೋಗ್ತೀನಿ ನಾನು. ಸೊ ಯು ಹ್ಯಾವ್ ಟು ಡೂ ದಿಸ್ ಇನ್ ಹಾಫ್ ಆನ್ ಅವರ್. ಇದು ಎಕ್ಸಾಮ್ 20-25 ಮಿನಿಟ್ಸ್ ಅಷ್ಟೇ ಟೈಮ್ ಇರುತ್ತೆ ಈ ಪ್ರಾಬ್ಲಮ್ಗೆ. 10 ಮಾರ್ಕ್ಸ್ ಇಟ್ಟು 20 ಮಿನಿಟ್ಸ್ ಮಾಡಬೇಕು. ZP ಹೇಳಿ, ಪ್ಲಾಸ್ಟಿಕ್ ಸೆಕ್ಷನ್ ಮಾಡೋದಿದೆ, ಕೋಡಲ್ಲಿದೆ. ನಾನು ಹೇಳಬೇಕು, ಪೇಜ್ ನಂಬರ್ 138 ಕೋಡ್ ಬುಕ್ಕು, ಸ್ಟೀಲ್ ಟೇಬಲ್ಲು, ಕ್ಯಾಲ್ಕುಲೇಟರ್ 3 ಇಟ್ಕೋಬೇಕು. ZP ವ್ಯಾಲ್ಯೂಸ್ ISLB 450 ಇದೆ, ಅಲ್ಲೇ ನೋಡಿ. ಯು ಶುಡ್ ರೀಡ್. ಎಲ್ಲ ನಾನು ಹೇಳಿದ್ರೆ ನೀವು ಹುಡುಕೋದಿಲ್ಲ. ಪೇಜ್ ನಂಬರ್ 138 ಇದೆಯಲ್ಲ, ಪ್ರಾಪರ್ಟೀಸ್ ಎಲ್ಲ ನೋಡಿದ್ರಲ್ಲ, ಅಲ್ಲೇ ZP ಇದೆ ನೋಡಿ. ZP Z ಅಂತಿದೆಯಲ್ಲ, ಪ್ಲಾಸ್ಟಿಕ್ ಸೆಕ್ಷನ್ ಮಾಡ್ಯುಲಸ್. ಎಷ್ಟದು? 1401.35 ಕರೆಕ್ಟಾ? ಇದು ಪವರ್ ಆಫ್ 3 ತಗೋಬೇಕು. 1401.35. So 1401.35 into 10 to the power of 3 millimeter cube. ನೋಡಿ ಅದು ಹಾಕ್ಬಿಟ್ಟು ಬೀಟಾ ಬಿ ವ್ಯಾಲ್ಯೂ 1 ತಗೊಳ್ಳಿ. ಪ್ಲಾಸ್ಟಿಕ್ ಸೆಕ್ಷನ್ ಆಗುತ್ತೆ. ಸೊ 1 ಅಂತ ಕೊಡಿ. ಸೊ ಅವಾಗ ಇದು ಲ್ಯಾಂಬ್ಡಾ LT ನಲ್ಲಿ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿ 1 into 1401.35 into 10 power 3 into 250 Fy ವ್ಯಾಲ್ಯೂ ಡಿವೈಡ್ ಬೈ MCR. ಇದನ್ನ ಹಾಕೊಳ್ಳಿ, ನ್ಯೂಟನ್ ಮಿಲಿಮೀಟರ್ ಹಾಕೊಳ್ಳಿ. 237.25 into 10 power 6 ಅಥವಾ ಬೇರೆ ಒಂದು ಅಂತ ತಗೊಳ್ಳಿ ಅಷ್ಟೇ. ಎಸ್, ಇದು ಸಿಂಪ್ಲಿಫೈ ಮಾಡಿ. ದಿಸ್ ಇಸ್ ಯುವರ್ ಲ್ಯಾಂಬ್ಡಾ LT, ನಾನ್ ಡೈಮೆನ್ಷನಲ್ ಸ್ಟ್ಯಾಂಡರ್ಡ್ನೆಸ್ ರೇಷಿಯೋ. Tell me the value. ಎಷ್ಟು? ವ್ಯಾಲ್ಯೂ ಬಂದಿಲ್ಲ, ಮತ್ತೆ ಚೆಕ್ ಮಾಡ್ಕೊಳ್ಳಿ. 1.21 ಇದೊಂದು ವ್ಯಾಲ್ಯೂ. ನೆಕ್ಸ್ಟ್ ನೀವು ಹಿಂದೆ ಹೋಗ್ಬೇಕೀಗ. ಅದರಿಂದ ಯಾವ ಭಾಗ ಇದೆ? 5NT ಅಂತ ಕೊಟ್ಟಿದೆ ಅಲ್ವಾ? 5NT is equal to ಆ ಫಾರ್ಮುಲಾ ಯೂಸ್ ಮಾಡಿ. ನೆಕ್ಸ್ಟ್ ಈಗ 4 ಆಯ್ತು 5 580 4 580 is equal to 0.5 into ಅಂದ್ರೆ ಇದು ಫಾರ್ಮುಲಾ 0.5 into 1 plus alpha nt into lambda nt minus 0.2 ಇದನ್ನ ಗಾರವಿದೆ plus lambda nt square ಇಲ್ಲಿ ನಮಗೆ alpha nt ಬೇಕು ಅದು ಕೊಟ್ಟಿದ್ದಾರೆ alpha nt ವ್ಯಾಲ್ಯೂ 0.21 for rolled steel section 0.49 for welded steel section ಇದು rolled steel section ಇದೆ ಅಂದ್ರೆ ಎಷ್ಟು ತಗೋಬೇಕು ನಾವು alpha nt ವ್ಯಾಲ್ಯೂ 0.21 ತಗೋಬೇಕು ಸೊ ಈಗ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿ 5nt is equal to 0.5 into 1 plus 0.21 into lambda nt is 1.21 ಬಂದಿದೆಯಲ್ಲ ಅದು minus 0.2 plus 1.21 square. Simplify this. This is 580. They are all numbers, non-dimensional numbers. What is the value? When the value is very small, take to more decimal places. Value is large, like 1000 to 2000. I will cut last one. But you cut this is next year. 580 Xi nt bending stress reduction factor. Xi nt formula is Xi. Greek letters is 5 Xi. Xi nt is equal to 1 divided by 580. The one relation is plus 580 plus 580 square minus lambda nt square. 580 square minus lambda nt square to the power of 0.5. Correct? This is formula. And this should be less than or equal to 1 per bit. So 1 divided by 580 is 1.338 plus 1.338 square minus 1.21 square lambda nt to the power of 0.5. This simplify this. So get the value of Xi nt. It is also just number, doesn't have any units. We take today. Point. 0.5 to 3. Less than 1.5. Less than 1.5. So next step. Sixth step. Next step. Above that. FPD. FPD is design bending compressive stress. FBD. Design bending compressive stress. So we are moving backwards. Arthaita? Idike formula kottidare ನಾವು ಏನು formula? FBD is equal to Xi nt Fy by gamma m. Xi nt into Fy by gamma m. ಇಲ್ಲಿ gamma m ಅಂದರೆ safety partial safety factor which is 1.1. Gamma 1 MO is 1.1. Substitute ಮಾಡಿ. Xi nt is 0.5238 into Fy is 250 divided by 1.1. ಇದು ನ್ಯೂಟನ್ ಪರ್ ಎಮ್ ಸ್ಕ್ವೇರ್ ಇರುತ್ತೆ ಸ್ಟ್ರೆಸ್ ಇದು. This is answer of FBD. Next last step MD. FBD आएगा MD. Stressing the moment. MD is given by beta B into ZP into FP. ನೋಡಿ ಮೇಲ್ಗಡೆ ಇದೆ ಫಾರ್ಮುಲಾ. ಕರೆಕ್ಟಾ? ಅಲ್ಲೇ ಕೋಡಲ್ಲಿ ಮೇಲ್ಗಡೆ ಫಾರ್ಮುಲಾ ಇದೆ ಅದು. MD is equal to beta B into ZP into FBD. ಇಲ್ಲಿ beta B ವ್ಯಾಲ್ಯೂ ಎಷ್ಟು ತಗೋಬೇಕು? ಪ್ಲಾಸ್ಟಿಕ್ ಸೆಕ್ಷನ್ ಇದೆ. ಸೊ ಅದಕ್ಕೆ 1 ಅಂತ ತಗೋಬಹುದು. So beta B value one compact metal plastic section you know. What do you mean plastic section, compact section? I have explained in those beginning videos 1 to 3. ಅದನ್ನ ನೋಡ್ಕೊಳ್ಳಿ. 1 into ZP value ಎಷ್ಟಿದೆ? ಅದು ಬರ್ತಿದ್ವಲ್ಲ 14 ಇರ್ತಾರೆ ZP 0.35 into 10 power 3 into FBD ಬಂದಿರೋದು 119.045. So this all these three you have to multiply. This value will be in Newton millimeter is units because it is moment Newton millimeter bending design bending strength bending and ಎಷ್ಟು ಬರುತ್ತೆ moment bending moment ಇದನ್ನ 10 power 6 ಹಾಕೊಳ್ಳಿ 10 power 6 ಗೆ ಬರುತ್ತೆ ನೋಡಿ Newton millimeter that is the equal to kilonewton. This is the final value. The answer, last answer. That means that is the design bending strength of that ISLP 450 when it is used as over a span of 4.5 meters. Span 4.5 meters is a section is to load tagolo is moment tagolutte anta that is the meaning. What is the value you got? 166.82. ಅದು ಕಿಲೋಮೀಟರ್ ಬಂದಾಗ ಅರ್ಥ ಆಯ್ತಾ? ಇಷ್ಟು ಸ್ಟ್ರೆಂತ್ ಬೆಂಡಿಂಗ್ ಸ್ಟ್ರೆಂತ್ ಅಷ್ಟು ಇಷ್ಟು ಇರುತ್ತೆ ಡಿಸೈನ್ ಬೆಂಡಿಂಗ್ ಸ್ಟ್ರೆಂತ್ ಫಾರ್ ದಟ್ ಬೀಮ್ ಸೆಕ್ಷನ್ ವೆನ್ ಇಟ್ ಈಸ್ laterally unrestrained over a span of 4.5 meter it can take a bending moment of up to this value 166.82 kilonewton meter. ಈಗ ಇದೇ ಪ್ರಾಬ್ಲಮ್ ಅಲ್ಲಿ ಸಪೋಸ್ ಲೋಡ್ ಕೇಳಿದ್ರೆ UDL ಕೇಳಿದ್ರೆ in case what is the load that beam can carry safe UDL it can carry ಅಂತ ಕೇಳಿದ್ರೆ ನೋಡಿ ಈಗ ಒಂದು ಕ್ವೆಶ್ಚನ್ ಆಡ್ ಮಾಡ್ತೀನಿ. Find the safe UDL the beam can carry. Find the safe UDL. This is additional ಕೇಳಬಹುದು. ಇದು ಡಿಸೈನ್ ಬೆಂಡಿಂಗ್ ಸ್ಟ್ರೆಂತ್. This value is your design bending strength. Only if they ask up to find the design bending strength, you can stop at this stage. Suppose if they ask you to find the safe UDL the beam can carry, additional what is the meaning of that? This is the beam. Suppose if this beam has to carry a load of W per unit length UDL, span L is 4.5 meters. So what is the value of W at that? That is the meaning. Just like that. How much load the beam can carry? Suppose if this section, if this beam is of ISLP 450, what is the load that can be applied? ಅದಕ್ಕೆ ಏನು ಮಾಡಬೇಕಂದ್ರೆ ಈ ಎಮ್ ಡಿ ನ ಮ್ಯಾಕ್ಸಿಮಮ್ ಬೆಂಡಿಂಗ್ ಮೂಮೆಂಟ್ ಈಕ್ವೇಟ್ ಮಾಡಬೇಕು. ಸೊ ಎಮ್ ಡಿ ಇಸ್ ಈಕ್ವಲ್ ಟು ಮ್ಯಾಕ್ಸಿಮಮ್ ಬಿಕಾಸ್ ಇಟ್ ಕ್ಯಾನ್ ಟೇಕ್ ಓನ್ಲಿ ಅಪ್ ಟು ದಿಸ್ ಬೆಂಡಿಂಗ್ ಮೂಮೆಂಟ್. Maximum of bending moment will occur here. You know that it occurs at the mid span. Illaguttalla maximum bending moment. Maximum bending moment. Formula ಏನು W F square by 8. inadequate points. 166.82 is equal to W into L is 4.5 W 10. That's all. If they ask you to find the load, equate maximum bending moment to MB. So it will be in kilonewton per meter. 166.82 into 8 divided by 4.57. Yeah, what is the answer? ಈಗ ಸೇಫ್ ಡ್ಯೂಟಿ ಅಂದ್ರೆ ಇದನ್ನ ಏನು ಮಾಡಬೇಕು ನಾವು 1.5 ಡಿವೈಡ್ ಮಾಡಿ ಆಯ್ತಾ ಫ್ಯಾಕ್ಟರ್ ಆಫ್ ಸೇಫ್ಟಿ ಫಾರ್ ರೋಡ್ 1.5 ಡಿವೈಡ್ ಮಾಡಿ ಎಷ್ಟೊಂದು ನೋಡಿ 42.43. This is the safe UDL that the beam can carry. If they ask UDL also, one more step we have to do. So these are we can find out the design bending strength of laterally unrestrained beam. Restrained, simple equation. Unrestrained, restrained is a formula. For restrained beam also this formula only, but here this FPD depends on so many parameters. Restrained is but anyway for you restrained beam is not there. The beam is open here. This is the entity law. So unrestrained is the market. So I have done two more problems. One I think two design problems in that earlier video. But anyway next class only I will design problem ಮಾಡ್ತೇವೆ ಇದನ್ನ ಬರಲಿಲ್ಲ ನಾನು ಮಾಡಿ ಹಾಕ್ತೀನಿ. ಸೊ ಇದು ನೋಡ್ಕೊಳ್ಳಿ ಅನಾಲಿಸಿಸ್ 10 marks to 12 marks ಕೇಳ್ಬೋದು. For design also we are doing in the same manner. What do we do? One extra step will be there in the case of design. Praveen, you have to see here, not there. When I am talking, you should see to me. Afterwards, I want available. I will tell when I have put the video or go through it. That's all. In design, what happens? Initially, we are going to assume some section, and that section is tested using these checks. In analysis problem, section will be given. Design problem only, they will give the load, they will give the span. You have to select the section yourself. After selecting the section, you have to check whether that section is safe or not. First step is called as preliminary design. After checking, it becomes the final design. Analysis will hagala. Section itself will be given. Span itself will be given. Directly, you have to check whether that section is safe or not. Design, you have to assume the section yourself. Then you have to check whether that section is safe or not. So same steps use ಮಾಡ್ತೀವಿ. ಇದಕ್ಕೆ ಮುಂಚೆ MCR ಅದನ್ನು find out ಮಾಡ್ತೀವಿ ನಾವು. MCR we are going to find out in the design problem also. But before finding MCR, that section we have to assume based on the value of ZP. ಇದರಲ್ಲಿ ZP value criteria design of the beams ಅಲ್ಲಿ ZP is a plastic section modulus. That is the main parameter in bending. Whereas in compression and tension members, area is the main parameter. We select the section based on the cross sectional area. Whereas in beams, we select the section based on the value of ZP. So this is what I wanted to tell. Okay.